The northern annular mode, also known as the Arctic Oscillation, involves low pressure over the Arctic Ocean and high pressure in mid-latitudes, positive mode, or vice versa, negative mode. It is represented throughout the troposphere. Thomson and Wallace first described it and showed that high-index, strong NAM days feature westerly feature winds along 55 degrees north and transpolar flow from Russia toward Canada, whereas low-index conditions are marked by cold anticyclones centered over central Canada and Russia, and an anticyclonic surface circulation throughout the Arctic basin. High index days are on average 5 degrees Celsius warmer over much of the Midwestern United States, central Canada, Europe, and the Barents-Kara Seas. Cold events occur with much greater frequency over North America, Europe, Siberia, and East Asia under low NAM index conditions. The NAM was mostly slightly negative from 1950 to 1990 and then mostly positive until 2008. The Southern Annual Mode, SAM, or Antarctic Oscillation, AAO, is the Southern Hemisphere counterpart of NAM, with opposing pressure and geopotential height anomalies over Antarctica and southern middle latitudes. The index was mostly negative from 1980 to 1993, positive to 2000, then negative to 2008. There is an increasing trend in the SAM in the austral summer since the mid-1960s, and its austral autumn since 1958. That has been linked to the intensification of the ozone hole in the stratosphere. The semi-annual oscillation is a feature of the mid-tropospheric circulation in the southern hemisphere. The mechanism involves the different annual cycles of air temperature between the Antarctica and the surrounding mid-latitude southern oceans. The temperature difference is strong at the equinoxes, particularly the autumn one in March. At latitude 50 degrees Celsius south, cooling in autumn is rapid compared with the warming in spring, September, the opposite being the case at latitude 65 degrees south. This behavior is related to the heat budget of the upper ocean. The semi-annual maximum temperature gradients in the mid-troposphere over the southern ocean through increased cyclonic activity shift the circumpolar trough poleward during the transition seasons. In turn, this produces a semi-annual oscillation in the pressure around 5 to 6 millibar and winds over the air affected by the troughs. The hemispheric mean pressure in mid-latitudes falls with the equatorial shift of the circumpolar trough from autumn to winter, while the pressure rises over Australia, South America, and southern Africa. The North Pacific Oscillation is the North Pacific counterpart of the NAO. It involves the Aleutian Low and the subtropical North Pacific anticyclone when the pressure gradient between them is pronounced. The mid-latitude westerlies are strong and more zonal across the North Pacific. It has major effects on air pressure in winter in Alaska. The Pacific Northwest, Canada, and the United States, and exceeds the effects of the PNA or ANSO. It also has greater influence on winter precipitation in the Pacific Northwest, western Mexico, and the south-central Great Plains. The NPO has fluctuated in sign over 10 to 15-year intervals. It was greatly positive from the mid-1980s to 1990s and then declined. It is also modulated by the Pacific Decadal Oscillation. The Pacific Decadal Oscillation PDO features warm or cool surface water in the North Pacific Ocean north of 20 degrees north during a warm positive phase. The West Pacific cools up to 0.05 degrees Celsius, and part of the Eastern Ocean warms during a cool negative phase. The opposite pattern occurs. The oscillation is quasi-periodic, each phase lasting for 20 to 30 years. Cool PDO regimes prevailed over 1890 to 1924, 1947 to 1976, except around 1958 to 1960, and since about 1998, while warm PDO regimes dominated 1925 to 1946 and 1997 through the late 1990s. The PDO is not a single mode of oceanographic variability, but arises through the combined influence of ANSO, atmospheric variability in the extratropics, and the North Pacific Ocean gyre. Extremes in the PDO patterns are marked by widespread variations in the Pacific Ocean, Pacific Basin, and the North American climate. The PDO has considerable influence on climate-sensitive natural resources in the Pacific and other North America, including the water supplies and snowpack in some selected regions in North America and major marine ecosystems from coastal California north to the Gulf of Alaska and the Bering Sea. In fact, it was fisheries scientist Steve Hare that coined the term Pacific Decadal Oscillation (PDO) in 1996 while researching connections between Alaska salmon production cycles and Pacific climate. Causes for PDO are not currently known. Likewise, the potential predictability for this climate oscillation is unknown. Understanding the mechanisms giving rise to PDO will determine whether skillful decadal along PDO climate predictions are possible, even in the absence of a theoretical understanding. PDO climate information improves season to season and year to year climate, whether skillful decadal long PDO climate predictions are possible. Even in the absence of a theoretical understanding, PDO climate information improves season to season and year to year climate forecasts for North America because of its strong tendency for multi-season and multi-year persistence. And let's move on. So the Pacific Decadal Oscillation was only identified by scientists in the 1990s, and we only have accurate observational data for identifying it going back some 50 to 60 years. Nathan Mantua and S.R. Hare from the University of Washington in Seattle described the operation of the Pacific Decadal Oscillation in the Journal of Oceanography in 2002. Mantua and Hare, 2002. Read more about the PDO from the Climate Impacts Group from University of Washington. So the PDO is detected as warm or cool surface water in the Pacific Ocean north of 20 degrees north. During a warm or positive phase, the West Pacific becomes cool and part of the Eastern Ocean warms. During a cool or negative phase, the opposite pattern occurs. It shifts phases on at least interdecadal timescale, usually about 20 to 30 years. The Atlantic multi-decadal oscillation is a mode of variability of SSTs in the North Atlantic Ocean, 30 to 65 north degrees. Analogous to the PDO, it was first identified in the 1990s. Since about 1860, it has oscillated with a period about 70 years. There was a warm phase in 1930 to 1960, and it was currently positive again. Its amplitude is about 0.04 degrees Celsius. There is debate as to how much is extremely forced and how much is due to internal variability. The signal of global warming has to be removed from the SST time series before it can be analyzed. Modes suggested that the MAO is caused by small changes in the North Atlantic thermal haline circulation. The signal appears to be linked to precipitation anomalies in North America, the summer climate of North America and Europe, and multi-decadal variations in droughts in the Sahara. Major droughts in the Midwest and the Southwest United States were more severe during the AMO warm phase in the 1930s and 1950s. It also has played a role in the formation of severe Atlantic hurricanes, suppressing their activity in the 1970s to 1990s cool phase. Atlantic multi-decadal oscillation was identified by Schneider and Ramkuti in 1994. So the AMO signal is usually defined from the pattern of sea surface temperature variability in the North Atlantic Ocean. Any linear trend has been removed. Its detrending is intended to remove the influence of greenhouse gas-induced global warming from the analysis. However, if the global warming signal is significantly nonlinear in time, not just a smooth linear increase, variations in the forced signal will leak into the AMO definition. Consequently, correlations with the AMO index may mask effects of global warming. In austral winter, May to September, 500 millibar geopotential heights over Africa exhibit positive correlation with heights over South America and the central South Pacific near New Zealand, and a negative correlation with height over the Southern Ocean. A wave number 3 pattern is apparent with 3 troughs and 3 ridges, showing the correlation of 500 millibar geopotential height anomalies in the subtropics with 500 millibar anomalies at 50 degrees south and 95 degrees east during winter.